universe is vast beyond measure. It stretches endlessly in every direction. A boundless expanse filled with mysteries that have captivated humanity for millennia. From the first stargazers who mapped the patterns of the night sky to the modern-day scientists peering into the depths of space with powerful telescopes, we have always sought to understand our place in the cosmos.
Let them get a view from there and see what the field of view looks like.
Yet, for all our progress, the universe remains largely unknown. Such conceptions, however, have always remained largely unheard of. The more we discover, the more questions arise. What is the nature of space and time? How did the universe begin, and what will become of it? Are we alone, or is life a common thread woven throughout the stars? Why make a difference? The boundaries of understanding. Humanity's understanding of the universe is shaped by the tools at our disposal. With each technological advancement, we gain a clearer view of the cosmos, uncovering secrets that were once hidden from us. When Galileo first pointed his telescope at the night sky, he revealed a universe far more complex than previously imagined. Moons orbiting Jupiter, craters on the moon, and countless stars invisible to the naked eye. Today, space observatories like Hubble and James Webb allow us to see galaxies billions of light years away, capturing light that has traveled for nearly the entire age of the universe. But even these incredible tools have their limits. The observable universe, the portion of the cosmos we can see, is bounded by the speed of light. Beyond this horizon lies the unknown, a realm forever out of reach because its light has not yet had time to reach us. Even within the observable universe, there are barriers to understanding. Some regions of space are shrouded in dense clouds of gas and dust, obscuring our view. Others, like the centers of black holes, are governed by conditions so extreme that our current physics breaks down. The universe is vast, but our perspective is finite. Our knowledge is shaped by what we can see, measure, and infer. And beyond that lies a vast expanse of mystery. Why space remains a mystery. Space is not just vast, it is extraordinarily complex. Understanding the cosmos requires piecing together clues from a wide range of disciplines, from physics and chemistry to biology and philosophy. Each discovery reveals new layers of complexity, often raising more questions than it answers. One reason space remains a mystery is its sheer scale. The universe operates on extremes, size, time, and energy, that are difficult for the human mind to comprehend. Galaxies span hundreds of thousands of light years, and the distances between them are even greater. The light we see from distant stars began its journey billions of years ago, offering a glimpse into the past, but leaving the present hidden. Another reason is the nature of the questions we ask. Many of the mysteries of space, such as the origin of the universe or the nature of dark matter and dark energy, lie at the intersection of the known and the unknown. They require us to push the boundaries of science, testing theories and models in ways that are often indirect and incomplete. For example, we cannot directly observe the Big Bang or the first moments of the universe. Instead, we study its echoes, such as the cosmic microwave background radiation, and use these clues to piece together a picture of what might have happened. But this picture is far from complete, leaving gaps that spark debate and speculation. This word presented this morning, I wonder if you could tell me the truth about the book you left at me, Alex asked. Space also challenges us with phenomena that defy our understanding. Black holes, with their immense gravity, warp space and time in ways that current physics cannot fully explain. Quantum mechanics, which governs the behavior of particles at the smallest scales, seems incompatible with the theory of general relativity, which describes the universe on the largest scales. Reconciling these two frameworks is one of the greatest challenges in modern science. The limitations of technology. This came out in 2010. While our technology has advanced dramatically, it still has limits. Telescopes can only observe what emits or reflects light, leaving vast portions of the universe, like dark matter and dark energy, completely invisible. Space exploration itself is constrained by distance and time. Even the fastest spacecraft ever built would take tens of thousands of years to reach the nearest stars. Our robotic explorers, like the Voyager probes, have given us incredible insights into our solar system, but they are mere pinpricks in the vast ocean of interstellar space. On Earth, particle accelerators like the Large Hadron Collider allow us to study the fundamental building blocks of the universe, but they can only reach energies far below those found in extreme cosmic environments, like the cores of stars or the collisions of black holes. The mysteries of space often require experiments that are currently impossible to perform. To truly understand phenomena like dark energy, we may need entirely new types of instruments, theories, and ways of thinking. The beauty of the unknown. Despite its challenges, the unknown is not something to fear, it is something to celebrate. The mysteries of space are a testament to the universe's complexity and beauty. They remind us that we are part of something far greater than ourselves, a vast and intricate cosmos that has existed for billions of years and will continue to evolve long after we are gone. The unknown inspires us. It drives us to ask questions, to build better tools, and to push the boundaries of our understanding. Each discovery is a step forward, a glimpse into the infinite possibilities of the universe. As we stand at the edge of knowledge, we are reminded that the journey of exploration is as important as the destination. The mysteries of space invite us to wonder, to dream, and to imagine what lies beyond the horizon. Space is not just a place of stars and galaxies. It is a realm of infinite questions. In the face of the unknown, we find not just answers, but meaning. For it is in our curiosity, our exploration, and our awe that we discover the essence of what it means to be human. The birth of the universe. What happened? The story of the universe begins with a singular moment, a moment that gave rise to all matter, energy, space, and time. We call this moment the Big Bang, a term that evokes the explosive and dramatic birth of the cosmos. Yet, despite decades of study, the details of this event remain one of the greatest mysteries of science. The Big Bang Theory is not so much a description of the universe's origin as it is a model for how the universe has evolved since its earliest moments. It tells us that the universe began in an extremely hot, dense state and has been expanding ever since. But what caused this expansion? And what, if anything, existed before it? These questions take us to the edge of human knowledge, where science intersects with the unknown. What is the Big Bang? The Big Bang is often misunderstood as an explosion, but it was not an explosion in space. Instead, it was an expansion of space itself. In the beginning, the universe was incredibly small and compact, a singularity where all matter and energy were concentrated in an infinitely dense point. In an instant, this singularity began to expand, creating the space and time that we experience today. This theory is supported by several key pieces of evidence, which has been one of the most compelling is the cosmic microwave background radiation, a faint glow of light that permeates the universe. This radiation is a remnant of the early universe, a snapshot of a time when the cosmos was only 3,8,000 years old. It tells us that the universe was once much hotter and denser than it is now. Another piece of evidence is the observation that galaxies are moving away from each other, as revealed by the redshift of their light. This indicates that the universe is still expanding, a phenomenon first discovered by Edwin Hubble in the 1920s. Yet, for all its explanatory power, the Big Bang theory leaves many questions unanswered. What came before the Big Bang? Perhaps the most profound question about the Big Bang is what, if anything, came before it. According to general relativity, the singularity at the beginning of the universe represents a point where time itself breaks down. This means that asking what came before the Big Bang may not even be a meaningful question. If time began with the Big Bang, then before has no context. Still, scientists and philosophers have proposed several ideas. One possibility is that the universe is cyclical, oscillating between periods of expansion and contraction. In this view, the Big Bang may have been preceded by a big crunch, where the universe collapsed in on itself, only to rebound and expand again. Another idea comes from quantum mechanics, which suggests that at extremely small scales, the universe might have been governed by quantum fluctuations. In this scenario, the Big Bang could have been a quantum event, a random fluctuation that caused a burst of energy and space-time to emerge. Yet another possibility is the multiverse hypothesis, which posits that our universe is just one of many, severely eliminated. In this view, the Big Bang was not the birth of all existence, but merely the beginning of our particular bubble universe. These ideas, while intriguing, remain speculative and untestable with current technology. The role of cosmic inflation. One of the most puzzling aspects of the Big Bang theory is how the universe became so large so quickly. To explain this, scientists propose a phenomenon called cosmic inflation, a brief period of exponential expansion that occurred within the first fraction of a second after the Big Bang. During this phase, the universe expanded at an unimaginable rate, growing from a size smaller than an atom to something the size of a grapefruit in less than a trillionth of a second. This rapid expansion smoothed out irregularities in the early universe, explaining why the cosmos appears so uniform on large scales. 2. While inflation solves several key problems in cosmology, it also raises new questions. What caused inflation to start, and why did it stop? The leading theory suggests that a hypothetical energy field, known as the inflaton field, drove this expansion. However, the nature of this field remains a mystery, and there is no direct evidence to confirm its existence. Even more intriguingly, some versions of inflation theory suggest that inflation may never truly stop. Instead, it could continue in distant regions of space, creating an infinite number of bubble universes. This idea ties into the multiverse hypothesis, suggesting that our universe is just one small part of a much larger, unobservable reality. Why did the universe expand? While the Big Bang describes how the universe has evolved, it does not explain why the expansion occurred in the first place. What caused the singularity to expand, and what provided the energy for this process? Some scientists propose that the expansion was driven by the release of energy from quantum fields. Others suggest that it may have been triggered by a process we do not yet understand, perhaps something rooted in physics beyond our current theories. One of the most intriguing possibilities is that the laws of physics themselves emerged during the Big Bang. In this view, the universe may not have needed a cause because causality, as we understand it, did not exist before time began. Unexplained uniformity. Another mystery of the Big Bang is the remarkable uniformity of the universe. On large scales, the cosmos appears almost perfectly smooth, with galaxies and clusters evenly distributed across vast distances. This uniformity is surprising because the universe's early conditions should have created much more variation. Why, then, is the universe so balanced? Inflation theory provides a possible explanation, suggesting that the rapid expansion of the early universe stretched out any irregularities, creating a smooth and uniform cosmos. However, this explanation relies on assumptions about the inflaton field that remain unproven. In Platon, the gospel of variable atoms, most of which fell when the electromagnetic waves from their working prints were encountered. Some physicists suggest that the uniformity of the universe may point to deeper principles of physics that we do not yet understand. Could there be a fundamental law that governs the structure of the cosmos, ensuring balance and harmony on large scales? Harris nodded. The limits of observation. One of the greatest challenges in studying the birth of the universe is the limit of observation. The earliest moments of the Big Bang are hidden from us because the universe was opaque during its first 3,800,000 years. During this time, light could not travel freely, as it was constantly scattered by charged particles. The cosmic microwave background radiation gives us a glimpse of the universe at the end of this opaque era, but it does not reveal what happened before. To study the first moments of the Big Bang, we would need to detect other forms of radiation or particles, such as gravitational waves from the early universe that are currently beyond our technological capabilities. The wonder of the unknown. The birth of the universe is a mystery that transcends science. It challenges our understanding of time, space, and causality, inviting us to explore questions that lie at the boundaries of knowledge. While we may never fully understand what happened during the Big Bang, the pursuit of this knowledge drives us to innovate, think deeply, and embrace the beauty of the unknown. Each discovery, no matter how small, brings us closer to understanding the cosmos and our place within it. The story of the universe's birth is not just a scientific puzzle. It is a reminder of the infinite possibilities that lie beyond our current understanding. It is an invitation to wonder, to explore, and to imagine what lies beyond the horizons of space and time. Dark matter and dark energy. The missing 95%. And when we look at the night sky, we see stars, galaxies, and clusters of glowing matter. These luminous objects give us a sense of the structure of the universe, revealing the vast cosmic web that connects galaxies across billions of light years. Yet, what we can see is only a tiny fraction of the total content of the cosmos. Incredibly, all the stars, planets, and galaxies, everything we have ever observed with telescopes, account for just 5% of the universe. The rest is invisible, made up of two mysterious components, dark matter and dark energy. Together, these unseen entities form 95% of the cosmos, shaping its structure, evolution, and ultimate fate. Despite their profound influence, dark matter and dark energy remain among the greatest enigmas of modern science. What are they made of? How do they work? And why do they dominate the universe while remaining hidden from view? What is dark matter? Dark matter is the invisible scaffolding of the universe. It is a type of matter that does not emit, absorb, or reflect light, making it completely undetectable through conventional means. We cannot see it or touch it, but its presence is unmistakable. The first hints of dark matter came in the 1930s, when astronomer Zwicky studied the Coma cluster of galaxies. He noticed that the galaxies within the cluster were moving much faster than expected, given the amount of visible matter present. Zwicky proposed the existence of an unseen dark matter to explain the gravitational pull holding the cluster together. Decades later, further evidence emerged from the work of astronomer Vera Rubin, who studied the rotation curves of galaxies. She found that stars on the outer edges of galaxies were moving just as quickly as those near the center, defying the predictions of Newtonian gravity. This implied the presence of a massive halo of dark matter surrounding each galaxy, providing the necessary gravitational force. Yet for all its importance, we still don't know what dark matter is. What could dark matter be made of? Scientists have proposed several candidates for the composition of dark matter, but none have been confirmed. One of the most popular hypotheses is that dark matter consists of dark gravitational particles, a type of particle that interacts only through gravity and the weak nuclear force. Despite extensive searches in underground laboratories and particle accelerators, no WIMPs have been detected. Axions. Axions are hypothetical particles that could solve both the dark matter mystery and certain problems in quantum physics. If they exist, axions would be incredibly light and weakly interacting, making them difficult to detect. Sterile neutrinos. These particles are a proposed extension of the standard model of particle physics. Unlike ordinary neutrinos, sterile neutrinos would not interact through the weak nuclear force, making them a possible candidate for dark matter, primordial black holes. Some scientists speculate that dark matter could consist of black holes formed in the early universe. These black holes would be too small to detect through traditional methods, but could account for the gravitational effects attributed to dark matter. Each of these candidates represents a fascinating possibility, but none have been definitively proven. The search for dark matter continues, driving some of the most ambitious experiments in physics. How do we know dark matter exists? Even though we cannot see dark matter, its effects are visible on cosmic scales. Without dark matter, galaxies would fly apart, as the gravitational pull of visible matter is not strong enough to hold them together. The observed rotation speeds of stars can only be explained by the presence of a massive, unseen halo of dark matter. Dark matter distorts the path of light from distant galaxies, a phenomenon known as gravitational lensing. By studying these distortions, scientists can map the distribution of dark matter in the universe, the patterns in the cosmic microwave background radiation, the afterglow of the Big Bang, reveal the influence of dark matter on the early universe. Without it, the large-scale structure of the cosmos would not exist as we see it today. Despite these clues, the true nature of dark matter remains elusive. What is dark energy? If dark matter is the glue that holds the universe together, dark energy is the force driving it apart. Discovered in the 1990s, dark energy is a mysterious phenomenon responsible for the accelerating expansion of the universe. This discovery came as a surprise. Scientists had long assumed that the expansion of the universe, set in motion by the Big Bang, would gradually slow down over time due to gravity. Instead, observations of distant supernovae revealed that the expansion is speeding up, as if the universe is being pushed outward by an invisible force. Dark energy is thought to make up about 68% of the universe, yet its nature is almost entirely unknown. What could dark energy be? Several theories attempt to explain dark energy, but none are conclusive. The cosmological constant proposed by Albert Einstein. The cosmological constant describes dark energy as a property of space itself. As space expands, more dark energy is created, driving further expansion. This explanation fits well with current observations, but leaves unanswered questions about the origin and magnitude of the cosmological constant. Quintessence. Some scientists propose that dark energy is a dynamic field, similar to the inflaton field that drove cosmic inflation. Unlike the cosmological constant, quintessence could vary over time and space, modified gravity. An alternative idea is that our understanding of gravity is incomplete. In this view, dark energy may not be a separate force, but rather a manifestation of gravity behaving differently on cosmic scales. Like dark matter, dark energy remains a profound mystery, challenging our understanding of the universe. Why do dark matter and dark energy matter? Though invisible, dark matter and dark energy shape the universe on the largest scales. Without dark matter, galaxies could not have formed. Without dark energy, the universe's fate would be entirely different. These two components are also deeply intertwined with the ultimate fate of the cosmos. Will dark energy continue to accelerate the expansion of the universe, leading to a big freeze? Or could its behavior change over time, resulting in a big rip or a reversal of expansion? Studying dark matter and dark energy is not just about understanding the unseen. It is about unraveling the very fabric of reality, the challenges of understanding the invisible. One of the biggest obstacles in studying dark matter and dark energy is their invisibility. These phenomena do not interact with light, making them impossible to observe directly. Instead, scientists rely on indirect methods, such as measuring gravitational effects or studying the cosmic microwave background. Another challenge is the scale of the problem. Dark matter and dark energy operate on cosmic scales, influencing the structure and evolution of the universe over billions of years. Reproducing these conditions in a laboratory is currently beyond our capabilities. Finally, our theoretical frameworks may be incomplete. Both dark matter and dark energy lie at the boundaries of known physics, suggesting that new theories or paradigms may be needed to fully understand them. The wonder of the unknown. The mysteries of dark matter and dark energy remind us of how much we have yet to learn about the universe. These invisible components, which make up the vast majority of the cosmos, challenge us to think beyond the visible and to question the very nature of reality. While the answers remain out of reach, the pursuit of understanding drives innovation and inspires awe. Each experiment, observation, and theory brings us closer to unveiling the secrets of the unseen, revealing a universe that is far stranger and more beautiful than we could ever imagine. Dark matter and dark energy are not just scientific puzzles. They are invitations to explore the unknown, push the boundaries of human knowledge, and marvel at the infinite complexity of the cosmos. The quantum universe, where physics breaks down. Beneath the familiar world of stars and galaxies lies a hidden reality, one that operates on scales so small they are almost impossible to comprehend. This is the quantum world, a realm where particles flicker in and out of existence, where matter behaves both as particles and waves, and where the rules of classical physics give way to something far stranger. Quantum mechanics is one of the most successful theories in science. It explains the behavior of atoms, electrons, and photons with astonishing accuracy, and it underpins much of modern technology, from semiconductors to quantum computers. Yet, for all its success, quantum mechanics is also deeply mysterious. It challenges our understanding of reality itself, leaving us with questions that defy intuition and logic. What is a particle? Does observation create reality? And how does quantum mechanics fit with the larger scales of the universe? These questions lie at the heart of the quantum universe, a domain where physics and our understanding of it begins to break down. Wave-particle duality. Two realities in one. One of the most famous and puzzling phenomena in quantum mechanics is wave-particle duality. In the quantum world, particles such as electrons and photons can behave both as discrete particles and as waves. This duality is best demonstrated by the double-slit experiment. When particles are fired through two narrow slits toward a screen, they create an interference pattern, as if they were waves passing through both slits simultaneously. But when the particles are observed, the interference pattern disappears. They behave as particles, passing through one slit or the other. This experiment raises profound questions about the nature of reality. How can a particle be in two places at once? And why does observation change its behavior? Scientists interpret this phenomenon using the concept of a wave function, a mathematical description of all the possible states a particle can occupy. The wave function collapses into a single state when the particle is measured. But what causes this collapse remains a mystery. Does the act of observation create reality, as some interpretations suggest? Or is there an underlying mechanism we have yet to discover? Quantum superposition. Existing in multiple states. In the quantum world, particles do not have definite properties until they are measured. Instead, they exist in a superposition, a combination of all possible states. Take the example of an electron orbiting an atom. Instead of following a single path, the electron exists as a cloud of probabilities, simultaneously in many places. Only when we observe it does the electron choose a specific location. This idea is famously illustrated by the thought experiment known as Schrödinger's cat. In this scenario, a cat is placed in a box with a quantum particle that has a 50% chance of triggering a deadly event. Until the box is opened, the cat is both alive and dead, a superposition of states. While this is a hypothetical scenario, it highlights the strangeness of quantum mechanics. Superposition is not just a mathematical abstraction. It has been observed in experiments, from electrons to larger systems like molecules. But why does superposition occur? And how does the universe transition from the quantum realm where superposition dominates to the macroscopic world where objects have definite properties? This remains one of the central mysteries of quantum mechanics. Quantum entanglement. Spooky action at the distance. Quantum entanglement is one of the most baffling and intriguing phenomena in physics. When two particles become entangled, their states are linked, no matter how far apart they are. If one particle is measured, the state of the other particle is instantly determined, even if they are separated by light years. This spooky action at a distance, as Albert Einstein called it, seems to violate the principle that nothing can travel faster than the speed of light, yet experiments have repeatedly confirmed the reality of entanglement. It suggests that particles are not truly separate entities, but are part of a deeper, interconnected reality. End of point, left and right. Read by Philip Goldsmith. What does entanglement mean for our understanding of space and time? Could it point to a hidden layer of reality, where all things are fundamentally connected? And how does this phenomenon fit into the larger framework of physics? These are questions that remain unanswered, challenging our understanding of the universe. The observer effect. Does observation create reality? In this observer effect, one of the most controversial and philosophical aspects of quantum mechanics is the observer effect. At the quantum level, particles exist in a superposition of states until they are observed. This raises a profound question. Does observation create reality? The Copenhagen interpretation of quantum mechanics suggests that the act of measurement collapses the wave function, bringing a particle into a definite state. In this view, the universe at the quantum level is indeterminate until it is observed. But what constitutes an observer? Does it require a conscious mind? Or can any interaction with the environment cause the wave function to collapse? Some physicists argue that observation is simply an interaction between a quantum system and a measuring device, with no need for consciousness. Others propose that consciousness itself plays a role, tying the quantum world to the mysteries of the mind. While the observer effect is central to quantum mechanics, its implications are far from clear. It challenges our notions of objectivity and reality, forcing us to rethink the relationship between the observer and the observed. Considerations: a quest for quantum gravity. In Children of God, there is a movement toward recognizing an agreement on what it means to be called Christian, a claim basic in nature and purpose. Likewise, the critique of illusion and false gravity. Quantum mechanics describes the universe at its smallest scales, while general relativity governs the largest, the stars, galaxies, and the fabric of space-time. Both theories are incredibly successful, but they are fundamentally incompatible. At the heart of this incompatibility lies the problem of quantum gravity. How can we unify the probabilistic nature of quantum mechanics with the deterministic framework of general relativity? One promising approach is string theory, which proposes that particles are not point-like but are instead tiny vibrating strings. These strings exist in multiple dimensions and could reconcile the two frameworks. Another idea is loop quantum gravity, which suggests that space-time itself is made up of discrete quantum units. Despite decades of work, a theory of quantum gravity remains elusive. Understanding it could unlock the secrets of black holes, the Big Bang, and the very fabric of the universe. But for now, it remains one of the greatest challenges in theoretical physics: the multiverse and quantum mechanics. Some interpretations of quantum mechanics suggest the existence of a multiverse, a vast collection of parallel universes. The many worlds interpretation posits that every possible outcome of a quantum event occurs, creating a new universe for each possibility. In this view, the universe is constantly branching into countless versions, each following a different path. While this idea is speculative, it provides a possible explanation for the randomness and probabilities of quantum mechanics. But if the multiverse exists, how could we ever test it? And what would it mean for our understanding of reality? These questions push the boundaries of science and philosophy, highlighting the profound implications of quantum theory.
It's almost
Why the quantum world is still a mystery. Despite its success, quantum mechanics leaves us with more questions than answers. The nature of reality. What does it mean for particles to exist in superposition or to be entangled? Are these phenomena hints of a deeper layer of reality, or are they fundamental to the universe? The role of observation. Does observation create reality, or is it merely a way of describing interactions? Could consciousness play a role in shaping the quantum world? The connection to the cosmos. How does quantum mechanics influence the larger scales of the universe? Could it hold the key to understanding the Big Bang, black holes, or dark energy? The wonder of the quantum universe. The quantum world is not just a realm of particles and equations. It is a source of wonder and inspiration. It reveals a universe that is far stranger and more beautiful than we could ever imagine, challenging us to rethink our assumptions about reality. While many questions remain unanswered, the pursuit of quantum mechanics has driven some of the most profound discoveries in science. It has expanded our understanding of the universe, revealing connections between the smallest and largest scales of existence. The mysteries of the quantum universe remind us that science is not just about finding answers. It is about embracing the unknown, exploring the boundaries of knowledge, and marveling at the infinite possibilities of the cosmos. Black holes and singularities, the edge of reality. In the vast and mysterious cosmos, few phenomena are as fascinating and perplexing as black holes. They are the universe's most extreme objects, where gravity reigns supreme, and the rules of physics as we know them cease to function. Born from the depths of massive stars, black holes are cosmic enigmas. They consume everything that comes too close, including light, leaving behind regions of space so dark and mysterious that even their edges, called event horizons, are shrouded in uncertainty. At their cores lie singularities, points of infinite density, where time and space collapse. What happens in these regions is beyond the reach of our current understanding, making black holes not just astronomical objects, but philosophical challenges. What are black holes? Black holes are formed when massive stars exhaust their nuclear fuel and collapse under the force of their gravity. If the collapsing mass is large enough, no known force can stop it, and the result is a black hole. A region of space where gravity is so intense that nothing, not even light, can escape. The boundary of a black hole is known as the event horizon. It marks the point of no return. Anything that crosses it is forever trapped. Yet despite their name, black holes are not entirely invisible. Matter falling toward a black hole heats up as it spirals inward, emitting intense radiation that can be detected by telescopes. Black holes come in various sizes, from stellar mass black holes a few times the mass of the Sun, to supermassive black holes millions or billions of times more massive. These giants sit at the centers of galaxies, shaping their evolution and dynamics. But while we have detected the effects of black holes, we cannot directly observe what lies within them. Their true nature remains one of the greatest mysteries in astrophysics. Singularities, the breakdown of physics. At the heart of every black hole lies a singularity, the point where matter is compressed to infinite density and the curvature of space-time becomes infinite. In this extreme environment, the laws of physics as we know them break down. General relativity, which describes gravity, predicts the existence of singularities, but it cannot explain what happens within them. The equations simply stop making sense. To understand singularities, we need a theory of quantum gravity, an as yet undeveloped framework that combines quantum mechanics with general relativity. What could singularities be? Are they truly points of infinite density, or do they represent a limit to our current understanding of physics? Some scientists propose that singularities might not exist in the way we imagine. Instead, they could be replaced by exotic structures such as quantum loops or fuzzballs, where the fabric of space-time itself becomes unstable. Without the ability to directly observe a singularity, these ideas remain speculative. Singularities are a reminder of the profound gaps in our understanding of the universe's most extreme conditions. The event horizon, the point of no return. The event horizon is the defining feature of a black hole, a boundary beyond which nothing can escape. It is often described as the surface of a black hole, but this surface is not solid. It is a region of space where gravity is so strong that escape velocity exceeds the speed of light. To an outside observer, an object falling toward a black hole would appear to slow down as it approaches the event horizon. Its light would become increasingly redshifted, fading into darkness. But for the object itself, time continues normally, carrying it inexorably into the depths of the black hole. The event horizon is not just a boundary, it is a gateway to the unknown. What happens beyond it is hidden from view, sealed off from the rest of the universe. This inaccessibility makes black holes both fascinating and frustrating, as we can only infer their properties through indirect observations. Light, the information paradox, a cosmic puzzle. One of the most intriguing mysteries of black holes is the information paradox. According to quantum mechanics, information about a physical system cannot be destroyed. Yet black holes appear to defy this principle by swallowing matter and, eventually, evaporating through a process known as Hawking radiation. Hawking radiation, proposed by physicist Stephen Hawking in 1974, arises from quantum effects near the event horizon. It suggests that black holes emit tiny amounts of energy over time, gradually losing mass and eventually evaporating completely. But if a black hole evaporates, what happens to the information about the matter it consumes? This paradox has profound implications for our understanding of physics. Does the information remain encoded in some way, or is it lost forever, violating the fundamental principles of quantum mechanics? Scientists have proposed several solutions, from the idea that information is stored in the event horizon itself to more exotic theories involving holography or alternate dimensions. Holography is indicated as a way of describing general features, such as the information refused by computers, including shadows. Scientists have proposed several solutions for alternate dimensions, but for now the information paradox remains unresolved, highlighting the limits of our knowledge about black holes and quantum physics. Black hole mergers and gravitational waves. In recent years, black holes have provided some of the most exciting discoveries in astronomy. In 2015, scientists detected gravitational waves, ripples in the fabric of space-time, for the first time. These waves were generated by the collision and merger of two black holes, each dozens of times the mass of the Sun. Gravitational wave astronomy has opened a new window into the universe, allowing us to listen to events that were previously invisible. By studying these waves, we can learn about the masses, spins, and dynamics of merging black holes, as well as the nature of space-time itself. But even as we learn more about these dramatic events, questions remain. What happens when supermassive black holes collide? Could such mergers produce new phenomena, such as wormholes or even baby universes? The study of black hole mergers is still in its infancy, leaving much to be discovered. Are black holes gateways to other realities? One of the most speculative and intriguing ideas about black holes is that they could serve as gateways to other parts of the universe, or even to other universes entirely. This idea arises from the mathematics of general relativity, which allows for solutions known as wormholes. A wormhole is a hypothetical tunnel through space-time that could connect distant regions of the universe. Some scientists speculate that black holes might be entrances to these tunnels, though they would likely be highly unstable. Other theories suggest that black holes could create new universes. In this view, the matter and energy consumed by a black hole might be recycled in a Big Bang-like event on the other side, giving rise to a new cosmos. While these ideas are purely theoretical, they highlight the profound possibilities that arise when we explore the edges of space-time. Black holes challenge us to think beyond the boundaries of our current understanding, imagining what might lie beyond. The role of black holes in the universe. Black holes are not just destructive forces. They are also creators, playing a central role in the evolution of galaxies and the cosmos as a whole. Supermassive black holes, which reside at the centers of most galaxies, are thought to regulate the formation of stars. Their immense gravitational pull shapes the motion of stars and gas, while their powerful jets influence the distribution of matter. Some scientists believe that black holes may have been essential to the formation of the first galaxies, providing the gravitational anchors around which stars coalesced. Others suggest that the growth of supermassive black holes and galaxies is deeply interconnected, with each influencing the other over billions of years. Understanding black holes is not just about studying isolated objects. It is about uncovering the forces that have shaped the universe itself, the limits of our understanding. Despite decades of research, black holes remain shrouded in mystery. Their extreme conditions challenge the limits of physics, leaving us with questions that may take generations to answer. This is what happens at the singularity. Does the singularity represent a true breakdown of physics? Or is it a clue to a deeper theory? If it were a real flaw, my experimental model would prove in the resume of science, ethics, specialities, and courses of individual experiences. What is the nature of the event horizon? Is information preserved on the event horizon, as some theories suggest? Could black holes be used for exploration? Are wormholes or other exotic phenomena real, and could they be harnessed for interstellar travel? With Dr. C. Ceremonenweiler, black holes push us to the edge of knowledge, forcing us to confront the unknown and question the very nature of reality. The wonder of black holes. Black holes are more than just astronomical objects. They are windows into the deepest mysteries of the universe. They challenge our understanding of physics, time, and space, reminding us of how much we have yet to learn. As we study black holes, we are not just exploring distant regions of space, we are probing the limits of human knowledge, seeking answers to questions that lie at the heart of existence. In the words of Patrick Swayze, black holes inspire awe, curiosity, and a sense of wonder. They are a testament to the infinite complexity of the cosmos, inviting us to explore, imagine, and dream of what lies beyond the edge of reality. The multiverse. Are we alone in a cosmic sea? As vast and infinite as the observable universe seems, many scientists believe it may be just one piece of an even greater puzzle. What if our universe is not the only one? What if it is part of a multiverse? A collection of countless universes, each with its unique properties, laws, and dimensions. The multiverse is one of the most provocative ideas in modern physics. It challenges our understanding of reality and raises profound questions about the nature of existence. Could there be other universes where the laws of physics are different? Could there be copies of ourselves living out different lives in parallel worlds? And if the multiverse exists, how could we ever hope to prove it? While the concept of the multiverse remains speculative, it is rooted in some of the most fundamental theories of science, from quantum mechanics to cosmology. It represents the ultimate frontier, a realm where imagination and inquiry collide. What is the multiverse? By Chris Diver. The term multiverse refers to the idea that our universe is just one of many. These universes could exist alongside ours, separated by vast distances, different dimensions, or entirely different realities. The multiverse concept arises naturally from several areas of physics, each offering a different perspective on how multiple universes might exist. Scientists have heard that actual universes could exist alongside ours, entirely different realities. The multiverse concept arises naturally from our multiple universes might exist, bubble universes. According to the theory of cosmic inflation, the universe underwent a brief period of exponential expansion shortly after the Big Bang. Some versions of this theory suggest that inflation never truly ends. Instead, it continues in distant regions of space, creating bubbles of universes, each with its unique properties. Our universe would be just one bubble in this vast, inflating sea, with countless others forming and evolving independently. The many worlds interpretation, quantum multiverse. In quantum mechanics, the many worlds interpretation proposes that every possible outcome of a quantum event occurs, creating a new universe for each possibility. For example, if you flip a coin, one universe would exist where the coin lands heads, and another where it lands tails. This branching process would result in an infinite number of parallel worlds, each slightly different from the others. Explanation stresses that universal genesis, most possible outcome of a quantum event, occurs in at least one dimension. String theory multiverse. String theory, which seeks to unify quantum mechanics and general relativity, predicts the existence of extra dimensions, beyond the familiar three of space and one of time. These dimensions could give rise to different universes with entirely different physical laws, where gravity, electromagnetism, and other forces behave in ways we cannot imagine. Gravity controlled how reality too expands in our heads through mathing. String theory, which seeks to unify quantum nice like a Victorian sofa, could be just what we need to elucidate the path. Mathematical universes. Some scientists propose that all mathematically possible universes exist. In this view, the multiverse is not limited to physical laws as we know them, but includes every conceivable reality that can be described mathematically. 2. Why do scientists take the multiverse seriously? The multiverse may sound like science fiction, but it is grounded in serious scientific theories. Many of the ideas that led to the multiverse, such as cosmic inflation, quantum mechanics, and string theory, are supported by strong mathematical and observational evidence. For example, the inflationary model of the universe has been highly successful in explaining the large-scale structure of the cosmos and the patterns observed in the cosmic microwave background radiation. If inflation is correct, the existence of a multiverse becomes a natural consequence, said Herman. Similarly, the many worlds interpretation of quantum mechanics offers a consistent way to explain the probabilistic nature of quantum events. While it is not the only interpretation, it is one that many physicists find compelling. The multiverse also provides potential answers to some of the most puzzling questions in cosmology. Why does our universe have the particular physical constants it does? Why are these constants so finely tuned to allow the existence of life? In a multiverse, these questions become less mysterious. If there are countless universes with different constants, it is not surprising that we find ourselves in one where conditions happen to be right for life. What would other universes be like? If the multiverse exists, the properties of other universes could be wildly different from our own, and the universes with different physical constants In some universes, the force of gravity might be weaker or stronger. Stars might burn out too quickly or never form at all. The balance between the strong nuclear force and electromagnetism might be different, preventing atoms from forming or creating exotic forms of matter. Universes with different dimensions. Some universes might have more than 3 spatial dimensions. In such a reality, the laws of physics as we know them would not apply. Objects might behave in ways that are impossible for us to visualize. They might be more tempting in the long run. For example, let's say 34,000 years ago, universes with different rules of time might flow backward, or it might not exist at all. These universes would challenge our most basic assumptions about causality and existence, universes with other forms of life. If the multiverse is infinite, there could be universes where life exists in forms completely alien to anything we know. Perhaps consciousness itself could emerge in ways we cannot imagine. The diversity of possible universes is both thrilling and humbling, a reminder of how little we truly understand about the nature of existence. Can we prove the multiverse exists? One of the greatest challenges of the multiverse hypothesis is that it may be inherently untestable. By definition, other universes would be separate from ours, making direct observation impossible. However, some scientists believe that indirect evidence might be found. For example, cosmic imprints. If our universe collided with another during its early expansion, it might have left detectable imprints in the cosmic microwave background radiation. Gravitational waves. The interactions between universes might produce unique gravitational wave signatures that could be detected by advanced observatories. Mathematical consistency. If the multiverse arises naturally from well-supposited theories, such as inflation or string theory, this could be considered indirect evidence for its existence. Even with these possibilities, proving the multiverse remains a daunting task. It challenges the very nature of scientific inquiry, pushing us to rethink what constitutes evidence and how we explore questions beyond our observable reality. Why does the multiverse matter? The multiverse is not just a scientific concept. It is a profound philosophical idea that forces us to confront fundamental questions about existence, our place in the cosmos. If the multiverse exists, what does it mean to be part of one universe among countless others? Does it make our existence less significant? Or does it highlight the uniqueness of our particular reality? The nature of reality, the multiverse, challenges our understanding of what is real. If every possible outcome exists somewhere, what does that mean for concepts like choice, free will, and identity, the search for meaning? For some, the multiverse offers a sense of infinite possibility, a reminder that the cosmos is far more vast and complex than we can imagine. For others, it raises questions about whether our universe is special, or just one of many random occurrences. The multiverse invites us to think deeply about our place in the grand scheme of existence, offering both wonder and uncertainty. The limits of our understanding. While the multiverse is a compelling idea, it also highlights the limits of human knowledge. Many of the questions it raises may never be answerable, either because of technological constraints or because they lie beyond the scope of science itself. The problem of evidence. Without direct access to other universes, how can we ever confirm their existence? Theoretical boundaries. The multiverse is rooted in theories like inflation and string theory, but these theories themselves remain incomplete and unproven. Philosophical challenges. Even if the multiverse exists, does it tell us anything meaningful about our universe? Or does it simply add layers of complexity? The multiverse is a reminder that some mysteries may remain forever out of reach, inviting us to embrace the unknown and to find beauty in the questions themselves. The wonder of the multiverse. The idea of the multiverse is both humbling and awe-inspiring. It reminds us that the universe we see is just a tiny fragment of a far greater reality, one filled with infinite possibilities and unimaginable diversity. Whether or not the multiverse exists, it challenges us to think beyond the boundaries of our understanding, to imagine worlds beyond our own, and to explore the deepest questions about existence. The multiverse is not just a scientific hypothesis. It is an invitation to wonder, to dream, and to embrace the infinite beauty of the unknown. The search for extraterrestrial life. Where is everyone? The universe is vast beyond comprehension. Our galaxy, the Milky Way, contains more than 100 billion stars, and beyond it lie trillions of other galaxies. Many of these stars are orbited by planets, and a significant number of those planets reside in the habitable zone, where conditions might allow liquid water to exist, a key ingredient for life as we know it. Given these staggering numbers, the likelihood of extraterrestrial life seems overwhelmingly high. And yet, for all our searching, the universe remains silent. We have detected no signals, found no visitors, and uncovered no definitive evidence that we are not alone. This apparent contradiction between the high probability of alien life and the lack of evidence for it is known as the Fermi paradox. It is one of the most profound mysteries of our time, forcing us to confront fundamental questions about life, intelligence, and the nature of the universe itself. The Fermi paradox, a cosmic silence. The Fermi paradox is named after physicist Enrico Fermi, who, during a casual conversation in 1950, asked, "Where is everybody?" He was referring to the apparent absence of extraterrestrial civilizations, despite the vastness of the universe and the seemingly high probability of their existence. Existential anxiety disorder, CHI. The word is famously used to refer to any pact of perfection that has occurred in human life, including mice and humans. Fermi's question becomes even more pressing when we consider the age of the universe. The Milky Way is about 13.6 billion years old, and Earth formed only 4.5 billion years ago. If intelligent life had emerged on other planets millions or billions of years before us, they would have had ample time to develop advanced technology and spread throughout the galaxy. Why then have we found no evidence of their presence? Is it possible that intelligent life is far rarer than we imagine? Or are we simply looking in the wrong way or the wrong places? The conditions for life. To understand the Fermi paradox, we must first consider the conditions necessary for life to arise. Life as we know it requires several key ingredients. Liquid water. Water is essential for the chemistry of life. It provides a solvent in which molecules can interact and form the complex structures necessary for biological processes. Planets in the habitable zone of their stars, where temperatures allow liquid water to exist, are considered prime candidates for hosting life. Organic molecules, the building blocks of life, such as amino acids and nucleotides, must be present. These molecules are relatively common in the universe, having been detected on comets, asteroids, and even in interstellar clouds. All right, what do we got facing us today? Energy. Life requires a source of energy, whether from sunlight, chemical reactions, or geothermal activity. Being a monk, while these conditions are necessary, they may not be sufficient. Even if a planet meets these criteria, the emergence of life depends on a complex series of events, many of which are poorly understood. The search for biosignatures. Modern science is actively searching for signs of life, both within our solar system and beyond. These efforts focus on detecting biosignatures, indicators of biological activity. Mars was once home to rivers, lakes, and possibly even oceans, making it a prime candidate for past or present life. Robotic missions, such as NASA's Perseverance rover, are exploring the planet's surface and searching for organic molecules, Europa and Enceladus. These icy moons of Jupiter and Saturn believed to harbor subsurface oceans beneath their frozen crusts. Hydrothermal vents on their ocean floors could provide the energy needed to support life. Exoplanets. The discovery of thousands of exoplanets, planets orbiting other stars, has revolutionized the search for extraterrestrial life. Instruments like the James Webb Space Telescope are analyzing the atmospheres of these distant worlds for signs of water, oxygen, methane, and other potential biosignatures. Despite these efforts, no definitive evidence of life has yet been found. Why haven't we found them? Several theories attempt to explain the lack of evidence for extraterrestrial life. The rare Earth hypothesis. This idea suggests that Earth is a unique combination of conditions, making the emergence of life, and especially intelligent life, exceedingly rare. Factors such as plate tectonics, the stable climate, and the presence of a large moon may be essential for complex life, but could be uncommon in the universe. The Great Filter. The zoo hypothesis? This theory posits that advanced civilizations are aware of humanity, but have chosen not to interfere, observing us from a distance like animals in a zoo. The Dark Forest hypothesis. Inspired by the work of author Liu Cixin, this hypothesis suggests that the universe is a dangerous place, where civilizations remain silent to avoid detection by potentially hostile aliens. We're looking the wrong way. Extraterrestrial civilizations may be using communication methods or technologies that we cannot yet detect. They may not use radio waves, or their signals may be so advanced that we fail to recognize them. The role of SETI, the search for extraterrestrial intelligence, SETI, has been at the forefront of the effort to find alien life. Using radio telescopes, SETI scientists scan the skies for signals that could indicate the presence of intelligent civilizations. One of the most famous efforts was the detection of the "wow" signal in 1977, a brief, unexplained burst of radio energy that has never been repeated. While intriguing, the signal remains inconclusive, and no other compelling detections have been made. In addition to radio signals, SETI researchers are now exploring other possibilities, such as laser communication, or even direct evidence of alien technology, known as techno-signatures. Could life be fundamentally different? But our search for extraterrestrial life is shaped by our understanding of life on Earth. But what if alien life operates on entirely different principles? Some scientists propose the possibility of shadow biospheres, forms of life that exist on Earth but are so different from known biology that we fail to recognize them. If such diversity exists on our planet, it could hint at even greater possibilities beyond Earth. Life might not require water or carbon at all. Some theories suggest that life could be based on silicon instead of carbon, or that it could thrive in environments we consider inhospitable, such as the methane lakes of Saturn's moon Titan. The potential for such radically different forms of life expands the scope of our search, but it also complicates it. How do we look for something when we don't know what it looks like? What if we are alone? While the search for extraterrestrial life is filled with hope, it also raises the unsettling possibility that we might be alone in the universe. If this is the case, it would mean that life on Earth is a unique and precious phenomenon. It would underscore the importance of preserving our planet and its ecosystems, as they represent a singular oasis in an otherwise lifeless cosmos. But being alone would also place a heavy responsibility on humanity. As the only known intelligent beings, we would carry the weight of representing life itself, a fleeting spark of awareness in an otherwise indifferent universe. The wonder of the search. The search for extraterrestrial life is not just a scientific endeavor. It is a profound exploration of our place in the cosmos. It challenges us to confront fundamental questions about existence, uniqueness, and connection. Whether or not we find evidence of alien life, the journey itself is a testament to humanity's curiosity and determination. It reminds us that we are part of a vast, mysterious universe, one filled with infinite possibilities and unanswered questions. The search for life is ultimately a search for connection, for proof that we are not alone in the vastness of space. And even in the absence of evidence, the act of searching brings us closer to understanding who we are and what it means to exist in this extraordinary universe. Time, a dimension we don't fully understand. Time is one of the most fundamental aspects of our existence. It governs everything we do, from the ticking of a clock to the evolution of galaxies over billions of years. Yet, for all its familiarity, time is also one of the greatest mysteries of the universe. What is time? Why does it flow in one direction? Is it an illusion created by our minds, or a fundamental property of the cosmos? And could time behave differently in other parts of the universe, or even cease to exist altogether? These questions lie at the heart of our understanding of reality, challenging both science and philosophy. Time is not just a measure of moments. It is a puzzle that defies easy answers, inviting us to rethink our place in the fabric of the universe. In time, the possibility of suicide is being reevaluated. What is time? Time is often thought of as a fourth dimension, alongside the three dimensions of space. Together, space and time form the fabric of the universe, known as space-time. This concept, introduced by Albert Einstein's theory of relativity, revolutionized our understanding of time. Einstein showed that time is not absolute. It can stretch and compress, depending on speed and gravity. For example, a clock on a speeding spacecraft will tick more slowly than a clock on Earth. Similarly, a clock near a massive object, such as a black hole, will run slower than one far away. This phenomenon, known as time dilation, has been confirmed by experiments and even plays a role in technologies like GPS. Thus the C-map. But while relativity explains how time behaves, it doesn't tell us what time is. Is it a fundamental property of the universe, or is it something we impose on reality to make sense of change? Some physicists argue that time may not even exist at the most fundamental level. In the equations of quantum mechanics, time often appears as an abstract parameter, not as a physical entity. This raises the possibility that time, as we experience it, is an emergent phenomenon, a byproduct of deeper processes we do not yet understand. The arrow of time. Why does time flow? One of the most intriguing mysteries of time is its direction. Time seems to flow inexorably from past to future, creating a clear distinction between what has happened and what is yet to come. This arrow of time is closely tied to the second law of thermodynamics, which states that entropy, a measure of disorder, always increases in a closed system. For example, a cup of coffee will cool over time, and a shattered glass will not spontaneously reassemble. This progression toward greater disorder gives time its direction. But why did the universe start in such a low entropy state, allowing the arrow of time to exist? And could time flow differently in other parts of the cosmos or other universes? Some theories suggest that the arrow of time is linked to the Big Bang, which set the initial conditions of the universe. Others propose that time's direction may reverse in certain extreme conditions, such as near a singularity or in a hypothetical contracting universe. The arrow of time remains one of the greatest unsolved puzzles in physics, challenging our understanding of causality and change. Time and relativity. Einstein's theory of general relativity revealed that time is not a universal constant, but a relative constant, It flows at different rates depending on an object's speed and the strength of the gravitational field it experiences. This phenomenon is most striking near black holes, where gravity is so strong that time nearly stops. For an observer far from the black hole, a person falling toward the event horizon would appear frozen in time, never actually crossing the boundary. But for the falling person, time would continue as normal, carrying them inexorably into the black hole's depths. These effects show that time is deeply connected to space and gravity, forming a dynamic and flexible fabric rather than a fixed backdrop. But they also raise profound questions. If time can stretch, slow, and even stop, is it truly fundamental? Or is it a property of space-time that emerges only under certain conditions, instead of creating it when needed to support a higher knowledge sense? But how can fractured time, if not self, arising from our strength, our ability, and our physicality? The nature of the present. Another mystery of time is the nature of the present. Why do we experience time as a series of now moments, each distinct from the past and the future? Some philosophers and physicists argue that the present is an illusion. In this view, all moments in time, past, present, and future, exist simultaneously, like the frames of a film reel. This concept, known as the block universe, suggests that time is not something that flows, but a static dimension in which all events are equally real. If this is true, then our perception of the present may be a result of how our brains process information, creating the illusion of a moving now. But if the present is an illusion, what does this mean for our understanding of free will, memory, and identity? And how do we reconcile this idea with our deeply felt experience of time's passage? I'm at the quantum level. In the quantum world, time behaves even more strangely. Quantum mechanics, which governs the behavior of particles at the smallest scales, challenges our classical notions of time and causality. For example, particles can exist in superposition, occupying multiple states simultaneously. They can also become entangled, with their states linked instantaneously across vast distances. These phenomena suggest that time at the quantum level may not flow in the same way it does in our macroscopic world. Some theories propose that time emerges from quantum processes, arising as a collective property of many interacting particles. Others suggest that time may not exist at all in the quantum realm, where events are governed by probabilities rather than sequences. Understanding the relationship between time and quantum mechanics is one of the greatest challenges in modern physics. It could provide insights into the nature of reality and the origins of the universe itself. Time in extreme environments. Time's behavior becomes even more mysterious in extreme environments, such as near black holes or during the early moments of the Big Bang. Near black holes. As mentioned earlier, time slows dramatically near a black hole's event horizon. This effect, known as gravitational time dilation, reveals the profound connection between time and gravity. But what happens to time inside a black hole, where space-time is stretched to its limits? Does time cease to exist, or does it take on a form we cannot yet understand? The beginning of the universe. During the Big Bang, the universe was in a state of extreme density and temperature. Under these conditions, the familiar flow of time may not have existed. Some theories suggest that time began with the Big Bang, making the question of before the Big Bang meaningless. These environments push the boundaries of our understanding, challenging us to rethink the nature of time itself. Could time be different elsewhere? If time is a property of space-time, could it behave differently in other parts of the universe, or other universes entirely? Some theories of the multiverse suggest that other universes could have different laws of physics, including different rules for time. In some universes, time might flow backward, or it might not exist at all. But if this is not possible, where does that leave life? Even within our universe, the concept of time becomes less clear on the largest and smallest scales. For example, in regions of cosmic voids, vast, empty spaces between galaxy clusters, Time may flow differently due to the absence of significant gravitational forces. These possibilities highlight the profound diversity of time's behavior, reminding us of how little we truly understand about this fundamental dimension. The limits of our understanding. Despite centuries of study, time remains one of the most elusive concepts in science. Alex sat aside, wondering whether there were anyone more in the center of the restaurant group. Philosophical questions. Is time real, or is it a human construct? Does it flow, or is it static? These questions challenge the boundaries between science and philosophy, revealing the complexity of time as both a physical phenomenon and a human experience. Scientific challenges. Understanding time requires reconciling quantum mechanics and general relativity, two theories that currently clash in their descriptions of the universe. Mateus arrived in Guadal to learn that the universe was just a giant network of interconnectedness, technological constraints. Studying time at its most fundamental level, such as during the Big Bang or inside a black hole, requires tools and methods that are currently beyond our reach. Time is a reminder of the limits of human knowledge, inviting us to explore questions that may never be fully answered. The wonder of time. Time is not just a scientific puzzle, it is a source of wonder. It connects the past, present, and future, shaping our lives and our understanding of the universe. As we explore the mysteries of time, we are reminded of the beauty of not knowing. Each question about time's nature and behavior opens the door to new possibilities, inspiring us to think deeply about the cosmos and our place within it. Whether time is fundamental or emergent, real or illusory, it remains one of the greatest frontiers of human inquiry. It is a thread that ties together all aspects of existence, from the smallest particles to the largest galaxies, reminding us of the infinite complexity and beauty of the universe. The structure and evolution of the universe. The universe is a vast and intricate tapestry, woven together by galaxies, stars, and the invisible forces that shape its structure. On the largest scales, it appears as a cosmic web, with clusters of galaxies connected by filaments of matter and separated by enormous voids. This grand architecture is both awe-inspiring and deeply mysterious, revealing the complexity of the cosmos and the forces that govern its evolution. How did the universe acquire its structure? What role do dark matter, dark energy, and gravity play in shaping it? And what lies beyond the boundaries of the observable universe? These questions take us to the heart of cosmology, challenging us to understand the universe as a dynamic and interconnected system. The large-scale structure of the universe. When we look at the universe on small scales, such as within a galaxy or a solar system, it seems chaotic and diverse. Stars form, planets orbit, and cosmic objects interact in countless ways. But when we zoom out, a remarkable pattern emerges. The universe is not randomly distributed. Instead, it forms a vast cosmic web, with galaxies clustering along filaments of matter. Between these filaments lie immense voids, regions of space that are nearly empty. This large-scale structure is thought to have originated from tiny fluctuations in the density of matter in the early universe. Over billions of years, these fluctuations were amplified by gravity, leading to the formation of galaxies, clusters, and superclusters. Most people thought that this pre-existing phenomenon had nothing to do with the cosmic consciousness or existence as we know it today. Yet the process by which this structure emerged is still not fully understood. The role of dark matter in structure formation. Dark matter plays a crucial role in shaping the universe's structure. Although it cannot be seen, its gravitational effects are essential for explaining how galaxies and clusters form and behave. In the early universe, dark matter began to clump together under the influence of gravity, creating dense regions where ordinary matter could gather. These regions served as the seeds for galaxy formation, with dark matter providing the scaffolding around which stars and gas coalesced. Without dark matter, the universe would look very different. The gravitational pull of visible matter alone would not have been strong enough to form the structures we see today. Galaxies might not exist, and the universe would be far less complex. However, the exact nature of dark matter remains a mystery. What is it made of? How does it interact with ordinary matter? And why does it dominate the mass of the universe while remaining invisible? These questions are at the forefront of cosmology, driving efforts to understand the unseen forces that shape the cosmos. The cosmic web, a universe connected. The cosmic web is one of the most striking features of the universe's large-scale structure. It consists of vast filaments of galaxies, connected by threads of matter and punctuated by massive clusters. These filaments are separated by voids, enormous, nearly empty regions that span millions of light years. The cosmic web is not just a visual pattern, it is a dynamic structure, shaped by the interplay of gravity, dark matter, and dark energy. Filaments and clusters. Filaments are the highways of the universe, where galaxies form and move under the influence of gravity. At the intersections of these filaments lie clusters, the most massive structures in the universe. Clusters are dominated by dark matter and contain thousands of galaxies, as well as hot gas that emits X-rays. Voids. Voids are regions of space that contain very few galaxies or stars. Despite their emptiness, they are an essential part of the universe's structure, acting as the negative space that defines the shape of the cosmic web. The formation of the cosmic web is a direct result of the universe's expansion and the distribution of matter after the Big Bang. Yet, many aspects of its evolution remain unclear. For example, how do dark matter and dark energy interact to shape the web over time? And what role do magnetic fields and other forces play in its development? The observable universe and its limits. The universe we see is vast, but it is not infinite. The observable universe is bounded by the speed of light and the age of the cosmos, limiting how far we can see. Light from the most distant objects has traveled billions of years to reach us, providing a glimpse into the universe's past. But what lies beyond the observable universe? Is the universe infinite, or does it have a finite size? These questions are difficult to answer as they depend on the universe's overall shape and topology. Flat, open, or closed? The shape of the universe is determined by its geometry, which can be flat, open, or closed. Current observations suggest that the universe is flat, meaning it will continue to expand indefinitely. However, this flatness is not absolute. It could change on scales beyond the observable universe, revealing a more complex structure. Successful lives are based upon it. Pierre Mathieu. What lies beyond? If the universe is infinite, it may contain regions that are completely different from the observable cosmos, with different physical constants or even different laws of physics. The limits of the observable universe remind us of the vastness of the unknown, inviting us to imagine what lies beyond the edges of our cosmic horizon. The evolution of the universe. The universe has undergone a remarkable evolution since the Big Bang, transforming from a hot, dense state into the intricate cosmos we see today. This evolution can be divided into several key stages: the Big Bang and inflation. The universe began as a singularity, expanding rapidly during a brief period of inflation. This set the initial conditions for the formation of matter and energy, the cosmic microwave background radiation. About 3,800,000 years after the Big Bang, the universe cooled enough for atoms to form, allowing light to travel freely. This light, now observed as the cosmic microwave background radiation, provides a snapshot of the early universe. The formation of galaxies and stars. Over hundreds of millions of years, gravity caused matter to clump together, forming the first stars and galaxies. These objects emitted light, ending the cosmic dark ages and illuminating the universe. The present universe, today, the universe is a dynamic and evolving system, with galaxies moving apart due to the influence of dark energy. In this sense, the goddess of suffering was no less powerful than that of the emperor. The evolution of the universe is a story of change and complexity, driven by forces we are only beginning to understand, the solved mysteries of cosmic structure. While we have made significant progress in understanding the universe's structure and evolution, many questions remain unanswered. What is the nature of dark energy? Dark energy drives the universe's accelerating expansion, but its true nature remains a mystery. Is it a constant property of space, or does it evolve? How do magnetic fields shape the universe? Magnetic fields are present throughout the cosmos, but their role in galaxy formation and cosmic structure is not well understood. It lies in the voids. While voids are largely empty, they may contain hidden structures, such as faint galaxies or intergalactic gas. Exploring these regions could reveal new insights into the universe's evolution. These mysteries highlight the complexity of the cosmos and the challenges of studying it on the largest scales. The wonder of the universe's structure. The structure and evolution of the universe are a testament to the beauty and complexity of the cosmos. From the smallest particles to the largest superclusters, the universe is a dynamic and interconnected system, shaped by forces that span billions of years and trillions of light years. As we study the universe, we are reminded of how much we have yet to learn. Each discovery opens new questions, inviting us to explore the unknown and marvel at the intricate patterns that define our cosmic home. The universe is not just a collection of stars and galaxies. It is a living story, one that continues to unfold, revealing the infinite possibilities of existence. Reflective conclusion, embracing the unknown. As we draw our journey through the cosmos to a close, we find ourselves standing at the threshold of the unknown. The universe, in all its vastness and complexity, is a place of infinite wonder and profound mystery. From the smallest quantum particles to the grandest cosmic structures, from the elusive nature of time to the silent voids between galaxies, the questions we have explored remind us of how much remains to be discovered. And yet, the mysteries of the universe are not obstacles, they are invitations. They invite us to ponder, to question, and to imagine. They remind us that the act of seeking is as important as the answers themselves, for it is in our search for understanding that we discover meaning, connection, and purpose. A journey through the cosmos. Throughout this exploration, we have ventured into the heart of the universe's greatest mysteries. We have asked questions that defy easy answers, touching on the fundamental nature of existence itself. We began with the origins of the cosmos, tracing the story of the Big Bang and the enigmatic forces that set the universe in motion. We marveled at the interplay of dark matter and dark energy, invisible forces that shape the cosmos on the grandest scales. We delved into the quantum realm, where particles flicker in and out of existence, and reality itself seems to blur. We contemplated the enigma of black holes, whose infinite gravity challenges the very fabric of space and time. And we asked whether we are alone in the universe, pondering the silence of the stars and the possibility of life beyond Earth. Each of these mysteries is a thread in the grand tapestry of the cosmos, a story that connects us to the stars and each other. The limits of knowledge. As we reflect on these mysteries, we are reminded of the limits of human understanding. For all our scientific advances, the universe remains far larger and more complex than we can grasp. Why does this vast expanse exist? Why does it follow the laws it does? And what lies beyond the horizons of our perception? These are questions that science may never fully answer, for they lie at the boundaries of knowledge, where reason meets imagination. Yet the limits of knowledge are not failures, they are opportunities. They remind us that discovery is an ongoing process, one that unfolds over generations and spans cultures, disciplines, and perspectives. To explore the unknown is to embrace uncertainty, and to acknowledge that the journey is as valuable as the destination. It is a humbling and inspiring reminder of our place in the cosmos, small but significant, finite but capable of infinite wonder. It's like time stands aside, like a connection. The universe is not just a collection of stars, planets, and galaxies. It is a story of connection. It connects the smallest particles to the largest structures, weaving together time, space, matter, and energy into a single, unified whole. As inhabitants of this universe, we are part of that story. The atoms in our bodies were forged in the hearts of stars billions of years ago, scattered across space, and brought together to form life. We are not separate from the cosmos. We are its conscious expression, capable of reflecting on its beauty and complexity. This connection across time and space is a reminder of the extraordinary nature of existence. It ties us to the stars, to the galaxies, and each other, forming a thread that stretches across billions of years and countless light years. The beauty of the unknown. There is a profound beauty in not knowing. The mysteries of the universe invite us to wonder, to dream, and to imagine possibilities beyond our current understanding. They challenge us to think deeply about our place in the cosmos, inspiring both humility and curiosity. The unknown is not a void, it is a canvas. It is the space where our imagination takes flight, where questions spark exploration, and where discovery begins. It reminds us that the universe is not just a place to be understood, but a source of endless wonder. Even as we seek answers, the act of questioning connects us to something greater. It is a reminder that the cosmos is not just out there, it is within us, shaping our thoughts, our dreams, and our aspirations. Our role in the universe. Footnote: the study of religion. As we look to the future, we must also reflect on our responsibility as inhabitants of this extraordinary universe. We are the only known life capable of understanding the cosmos, the only beings who can ask these profound questions. What will we do with this gift? Will we use our knowledge to preserve and protect the fragile oasis of Earth, the only home we have ever known? Will we venture beyond our planet, carrying the spark of life to the stars? The answers to these questions will shape the future of humanity and our place in the cosmos. They remind us that exploration is not just a scientific endeavor, it is a moral and philosophical one, tied to our values, our aspirations, and our sense of wonder. The universe as a mirror. The universe is more than a collection of mysteries to be solved. It is a mirror that reflects our deepest questions about existence. As we gaze into the cosmos, we are not just looking outward, we are looking inward, exploring what it means to be human. The search for answers is also a search for meaning, for a sense of connection to something greater than ourselves. Each question we ask about the universe is a reflection of our curiosity, our creativity, and our desire to understand the world around us. It is a testament to the power of the human spirit, a reminder that even in the face of the infinite, we are capable of wonder. An invitation to wonder. As we conclude this journey, let us take a moment to marvel at the infinite possibilities of existence. The universe is vast, complex, and mysterious, filled with questions that may never be fully answered. But it is also beautiful, inspiring, and deeply meaningful. The mysteries of the cosmos are not barriers, they are invitations. They invite us to explore, to imagine, and to connect. They remind us that the universe is not just a place we inhabit, but a story we are part of, one that continues to unfold with each discovery. As we stand at the edge of the unknown, let us embrace the wonder of not knowing. Let us celebrate the questions that drive us to seek, to learn, and to dream. For in the vastness of the cosmos, it is our curiosity, our imagination, and our sense of wonder that truly make us extraordinary. Closing reflection. The universe is not just a collection of stars and galaxies. It is a place of infinite possibility, a reminder of the beauty and complexity of existence. As we gaze into the depths of space, let us remember that we are part of this grand story, connected to the stars and each other. The questions we ask may never have definitive answers, but they are a testament to the power of the human spirit, a spirit that seeks wonders and dreams. For in the face of the unknown, we find not just knowledge, but meaning. We find not just discovery, but connection. And we find not just answers, but the infinite beauty of existence itself. Denkon, a song of peace.